So she wrote her own code to do simulation of flow around the cylinder, kind of like the first tutorial that you did. In that first tutorial, there wasn't any unsteadiness in the flow, but this is what it typically looks like. So there's typically vortices that get shed behind the flow. So the top figure there is the velocity magnitude contour. So you can see those vortices being shed. The middle figure is the vorticity. So again, the middle figure is a diverging color map because we want to show positive and negative vorticity. That basically tells us the direction of rotation of each of those vortices coming off of this cylinder. The bottom figure, which I have in more detail on the next slide, is the velocity vector plot. So you can't really see it that well because of the fantastic resolution of that projector, but I have a zoomed in. So this is what you would say is an Eulerian view of the velocity vector field. So the vector is each kind of point has a velocity vector, and you can see as the vortices kind of come off, they go through the flow field, the local direction of the velocity vectors here. So that's an example of an unsteady flow field. So at each instant in time, if you were to pause it and draw lines that were tangent to each of those velocity vectors, you would get your streamlines. And here we have a sequential color map because we're just looking at the magnitude. So each vector is the same size. There are many different ways to visualize kind of vector magnitude, and it's a little bit of an art, but I think this is nice because each vector is the same size, so they're not scaled by magnitude. They're colored by magnitude though. So it's easy to see the direction, and then the color gives you the velocity magnitude. So the plan for today is to finish the post-midterm review, and I'm going to do an example on conservation of momentum, which is the question you had in tutorial 10. I also want to do a clarification about some of the control volumes we did in examples in module 5. So there's some subtleties that I didn't do a good enough job pointing out that I want to point out this lecture. Just course reminders. So you have your tutorial 11 tomorrow. That's going to be a non-uniform conservation of momentum problem. So really similar. It kind of builds on that airfoil, or I think I did an ellipse in class. The case where you have a linear velocity deficit that you assume. So it's going to be similar to that. So definitely take a look at that example before the tutorial tomorrow, and you should be fine. The project's also due tomorrow, which hopefully isn't news to you. Um, and yeah, the course feedback is open right now. I gave some time last lecture to complete that, but please complete that by April 8th. Any questions on course delivery? Another reminder, so no lecture next Monday. We're just going to have one lecture on Friday, so there's no makeup or anything on Friday. It's just regular time on Friday. Any questions? So last lecture we reviewed module 4, which was Bernoulli's equation and how we extend it to internal flows. I'm going to review module 5 today, which is on conservation laws. Okay, so I'll give kind of the relation that we covered, and I'll also talk about common mistakes or notes about these relations. So for conservation of mass, in words, we said that the conservation law for conservation of mass says accumulation equals net flux into RCV. It makes a lot of sense. So if the net flux is positive, we expect our control volume to be accumulating mass. And if the net flux is negative, then we expect our control volume to be losing mass. If the net flux is 0, then the accumulation is 0, so the control volume's mass doesn't change. So we had this relation. So that volume integral is the accumulation term. So what this volume integral is, if you integrate, remember density is mass per unit volume, right? So kilograms per meters cubed. So if you do a volume integral of the mass per unit volume, you kind of eliminate that volume and you're left over with just mass. So this term is just the mass, and then we take the time rate of change of the mass in our CV. That's equal to the net flux in. So that's going to be an area integral of the flux along every single small area element on the outside of our CV, which is rho v dot n hat dA. So this, remember the mass flow rate, m dot is rho VA. So that's all this is it's a rho times some sort of velocity times an area. So if you do that integration, sum that over all the dAs that are your control surface, you get the net flux. However, because of this, the definition of n hat, remember that n hat always points outward from the CV. This actually gives you, this term alone gives you the net flux out. So if you put a negative there, you get the net flux out. So the common mistakes here, I would say, come from v dot n hat. So it's important to remember that n hat always points outward from the control volume. So if you have a box like that, and that's our control volume, on each of these surfaces, the n hat will do this. So on the left-hand side, n hat would be like a negative x, and on the right-hand side, n hat would be positive x. Similarly for the y's. So that dot product actually tells us the kind of projection of the velocity vector onto this normal vector. And both of these vectors are defined using the global coordinate system. So really the sign of that, all that does is it tells us the relative direction of the velocity compared to the local normal vector. So I'm also going to give you those kind of shortened formulas, but I'll put a little asterisk. You should know that there's some restrictions. So that asterisk for those will be steady state. With constant or average inlets and outlets. So the reason that those assumptions are useful is when it's steady state, this term becomes zero because it's partial by partial t, so there's no time rate of change. The constant average inlets and outlets means we don't have to evaluate an area integral. So basically, the velocity will be constant with respect to area. So this turns into a much more, I guess, familiar version of conservation of mass, which is summation over outlets minus the summation over inlets is equal to zero. The common mistakes with this one, so the negatives, the signs, the coordinate system, all that has been already accounted for in this. So that's where this negative comes from. So these m dots is rho. You can think of it as rho times the magnitude of the velocity times a. Technically, this is the this magnitude is the normal velocity magnitude, but it's always normal, right? So we always have flow directly into the CV. At least in this class, we're always going to have flow directly into the CV. You're not going to have to worry about some sort of oblique flow. We've never done an example like that. M dot is rho VA, so I'm not sure how to put this. Don't make M dot negative. So don't worry about the signs. Just make sure that everything in the inlet is in front of this negative sign, right? If that's confusing, please let me know. Just don't worry too much about the signs of these M dots. Okay, so any questions on conservation of mass? Okay. Now we'll do conservation of momentum. So the kind of word relation for conservation of momentum is that the rate of change of momentum in our control volume is equal to the net force. So that's Newton's second law. The integral relation is this. So it's the volume integral of the momentum in our CV. So rho v, I'll draw these, rho v dv. So again, if you ignore this partial by partial t, this is the volume integral of our CV's momentum. So you're not used to having to integrate to get momentum. It's normally just kind of mass times velocity. But we have to account for our CV might have different velocities throughout it. So we have to do a volume integral in order to get the CV's momentum. The partial by partial t is the time rate of change. So that's one way that our CV can change momentum. Another way that our CV can change momentum is by flow going in or out of it. So that flow carries momentum. So the flux of momentum through our CV's control surfaces is this. So all that is equal to the sum of forces on our CV. So this is the net momentum flux. So it's kind of like the small mass flux coming into our CV has a certain velocity. So it's going to carry momentum in or out of our CV. That's kind of what Reynolds transport theorem is. It's hard to think about something carrying momentum, but I guess everything carries momentum, like every moving mass carries momentum. It has momentum. You can think of it as also carrying momentum into our CV. So we have to account for that in our CV's momentum balance. So is this equation a scalar or vector equation? Take a guess, someone. Vector, yeah, vector. So conservation of momentum is a vector equation. So that I'll say that that's a common mistake. So the vectors in this equation are the red terms here. So I'm not sure how much in other courses you've talked about like dimensional compatibility between terms in an equation, but in a vector equation, every term should be a vector. So the first term is a vector, and it's a vector because of that v. The second term is a vector because of this v. So this v is a scalar. And then obviously the sum of forces is going to be a vector. There's nothing complicated there. So we expect every single term in this equation to be a vector. And also every single term should have the same units. So every single term in this equation actually has the units of newtons in like SI units. So this, for example, the partial derivative of that volume integral of rho v dv, that's just newtons. So that's just a newton, something in units of newtons. Okay. Another common mistake with this equation would be the same from above. So that note about v dot n also applies. And remember, v n hat f, these are all defined based on the global coordinate system. So the easier to use version of this equation, I forgot to put a star in this one. So remember, this equation is that star above, steady state, constant, average, inlets, outlets. That is for this equation. So this equation doesn't apply in that case where we have the velocity deficit. That's the case you'll see in your tutorial tomorrow. You can, if you want, use it sort of on the left-hand side face of that CV. So the CV looks, if you remember the question, the CV looks something like this. So on the left-hand side face, you have a constant velocity profile, so you can do just m dot rho VA there. But on the right-hand side face, you have to do the integration. Okay, anyways, the version of that equation for conservation of momentum is this. Okay, there's a lot of notes. Okay, so sum of m dot v out minus the sum of m dot v in is equal to the net force. So where this equation comes from is if you the red terms in the second equation are the same red terms from the above equation. So when you do that volume integral, if the when you do that volume integral, the volume integral of rho dv, it just gives you, sorry, that first term is 0 in the second equation because of the steady state assumption. So we're only, both of these terms on the left-hand side here, both of these terms come from this term. So the v there is the same v vector, and this rho v dot n, that's just m dot. It's actually what we get in the conservation of mass. So the area integral of rho v dot n is just m dot. Okay. Yeah, so the common mistakes / notes for this equation would be, again, a vector equation. With m dot, that's the same as from above. So don't worry about the sign of m dot. But the vectors in this equation, everything that's in red, so v and f, we need to worry about sign. So that's a common error, is a sign error in the v's. So if you have an inlet that's in the negative x direction, this whole thing would be negative, so you get negative, negative there. So just use the equation. I don't know how to say it more simply. Just use the equation as it's written and be really careful about the signs on anything that's a vector. It sounds simple, but there's a lot of, I guess, mistakes being made about this. So the force is the FP pressure force. So we need to worry about the sign of our pressure force because it's a force, and we determine the sign by knowing that pressure force always points into the CV. It is also defined based on the global coordinate system. So any questions about use of this equation? The example that I'm going to go through today, I'll point out it has all of these common errors, but any questions about this? The last integral relation we talked about was Reynolds transport theorem. It says that dn by dt partial by partial t of the volume integral rho eta dv plus this area integral. So the notes about this equation: eta is sort of big N per unit mass. So remember what I said before as well about dimensional, it's called dimensional homogeneity in an equation. So the left-hand side has units of sort of n per unit time. So each of these terms is just going to be a units of big N per unit time. So these equations, even though they have eta in them, they're a volume integration or an area integration of eta. So each of these equations here, for example, this has units of n. It doesn't have units of eta. Does that make sense? Yep.
The eta thing at the end, that isn't supposed to be part of the equation, that's just a note, right?
Yeah. Yeah, I can move it down. Yeah. So let me just say that again. So this here has units of n. You can think of the units. So an integral is just a sum. I don't know if anyone ever told you this is just a fancy s. That's what the integration sign is. That's why they came up with it. They're not that creative. So the units of this will be units of n. So we expect, for example, kilogram per meters cubed times n per kilogram times meters cubed. These are the terms in each of this. These are the three terms. And then we just sum that. That's what an integral is. So this will have units. Again, I'm just doing this integration before we take the partial derivative. Does that make sense? So this whole thing has units of n. This mass flux here will have, it's sort of a n flux, n per, big N per unit time. Okay, so each term has units n per second. Let's use seconds for the time unit. So it's a time rate of change of n in our CV. Last point is if eta is a vector, this is a vector equation. So for example, that's how we derive conservation of mass from this, or sorry, conservation of momentum from this equation. So we put eta is equal to the momentum per unit mass, which is just v. So any questions about Reynolds transfer theorem? So I'll go through the setup of the solution for tutorial 10. So this is basically a piping system with a whole bunch of inlets and outlets. And our job is to do these summation signs across this. So I don't want to do an area integral over this horrible looking piping system, so we're just going to do this. But that requires us to assume something. So we have to say in our solution, and I'll give you the hint on the final that you should give this, because I know you guys know what to say. We have to assume that a steady state. Okay. So I also gave kind of a tabulation of a bunch of different pressures and flow rates in the system. So the flow rate, I think the question asked for one, we have to determine this m dot, and also to determine, so the question I think said determine m dot 2 and the net force. Okay. So the first step, when there's a unknown mass flow rate, you have to use conservation of mass. So summation of m dot out minus summation of m dot in equals 0. Okay, so remember I said we don't have to worry too much about the signs for these m dots. We can just use these m dots as they are. So the sign has already been accounted for in this equation. So we have to basically determine now in this table, I'm going to say a direction, whether these are going to be in or out. Okay, so our control volume for this question, something I want to emphasize. So our control volume is sort of this bubble that hugs every single one of these pipes. So that's going to be incredibly hard for me to draw. But you can think of it like if you took, you know, the CAD operation that you just do like an offset from a surface and it just like puts it a little bit outside the surface. It's just like that operation over this whole pipe. And the reason that our control volume encompasses this pipe is that we want to determine the net forces on this pipe, and we can't neglect friction at the walls. So our pipe is part of the control volume because the forces applied to that pipe will be the forces on our control volume. Okay? Was that confusing how I explained we're doing the control volume? It's just like a bubble. All of this, every single little bit of piping would just extend a little bit, and then we know exactly at the inlets and outlets, our bubble kind of does that, so we know we have inlets and outlets there. Okay. So the direction of 1 is going to be out. So the arrows here show the directions, right? So 1 is going out of RCV. 2 is an unknown. So we're saying out. 3 is in. 4 is out. 5 is in, or I've gotten misaligned. Five is in, 6 is out. Good. So we're just gonna stick the magnitudes of these m dots into the summations. I'm gonna just double check this. 1, 2, 4. Okay. So that will be m dot 1 plus m dot 2 plus m dot 4 plus m dot 6 minus our inlet summations, which is m dot 3, m dot 5 equals 0. Okay, so we can, the only unknown here is m dot 2. Like if you look here, we have one equation, one unknown, so we can solve. So it's 40 kilograms per second. So any questions on the mass flow rate summation? Now the conservation of momentum is where I saw most errors being made in the tutorial solutions. So I think it's a mix of conceptual understanding and a mix of just not being careful with the signs. Okay, so the equation I gave was out. Sorry, the momentum flux out minus the momentum flux in equals. So what I'd suggest is we just assume the forces as positive, and then interpret the signs that way. So I don't think we directly know from looking at this thing what direction the net forces to support this piping system will be. So we're just going to assume them as positive. Again, our control volume will encompass our pipe so that we get the forces on the pipe. Okay, so let's look. Okay, so the x direction, we need to worry about anything that has a vector component in the x direction in this equation. Okay, so let's go to our, you guys are good. So let's go to our figure. So the coordinate system is given here. So anything that has a vector component along this direction, we need to account for in this balance. So I gave the projected views here. So this is looking at this projected view is looking anything, this is basically the x z plane. So R3 is in the x, we have a component of 1 in the x, and so 1, 3, and 6 are affected in the x. Okay, so the m dot is just m dot. You don't need to worry about vector components, signs, anything like that. So we have m dot 1, m dot 1. Remember I said you need to worry about the v's in this equation. So R1, our flow in the 1, has it has a positive x component like that of basically it would be V1 cos 60 because I gave you the angle here that pipe makes. And that's again positive because we're in the positive x direction. And dot 1 V1 cos 60. We're still doing the out. We're still doing this first term. Okay, so let's look. The other outlet we have in the x direction is 6. So again, we don't worry about signs. It's just m dot 6. Now, what is it positive or negative v6? Yep. Negative, because it's in the negative x direction. So remember the v in this equation, we need to worry about the signs. So m dot 6 times negative v6. Okay. That's all of the outlets we have that have a vector component of v in the x direction. Now we have minus the next summation. So the inlets in the x direction, we have 3, and there's no other inlets in the x direction. These are both outlets. So minus m dot 3. What about the sign of v3 here? Anyway, the sign of v3 here. I'm gonna wait till someone gives a confident answer. Yeah, negative. Yes. Okay. It's negative because this arrow points the opposite direction of the x-axis, right? It's in the negative x direction. So it would be negative v3. Okay, so that's been pretty illustrative example here. We're just doing the left-hand side of the x direction. So we need to look at all the vectors that have vx, and the signs of the v's here will be given based on the global coordinate system. We don't worry about the signs of m dots, and in some cases we have to project the x component. We have to get the x component because our thing leaves kind of at an angle. Now, the forces in the x direction will be Fx, that's kind of our piping force. And we're going to have 3 pressure forces. So we have 1, 3, and 6. So we'll have a pressure force corresponding to each of those. So at 1, what direction does the x direction pressure force point? Is it positive or negative?
It's opposite of the direction.
Exactly. You can think of it that way. So it's opposite of for that case, opposite of the direction of the flow. That's just for an outlet though, right? For an inlet, it would be the same direction as the flow, like for here, right? So the pressure force always points into the CV. So forget about, when they're on the right-hand side, forget about your inlets and outlets and things like that. Just think about the pressure force points into the CV. So always pressure force into the CV, regardless if it's an inlet or an outlet. So pressure force into the CV, if I go to our front view, into the CV there, looks like this. So it's going to have that positive x direction component. Sorry, did I say positive? Yeah, I meant negative. Negative x component. So P1A1, negative P1A1 cos 60. Okay, the next thing we have to worry about in the x direction is the pressure force from 3. So remember, pressure force always points into the CV. So that will be in our negative x direction as well. Minus P3A3. Okay, we have one more, and that's 6. So 6, pressure force points into the CV, and that's in the positive x direction, right? Plus P6A6. This equation is basically set up now for you to be able to solve the problem, assuming no calculator errors are made. You have to do one extra step though, and that's that VI is going to be M dot is rho VA. So V is going to be M dot over rho A. So it's an incompressible flow, which means there's no rho I. We just have constant density. So when you do that, which I provided all the information to do that, you have the only unknown in this equation is Fx. So are there any questions about the sign thing? I'm not going to do the other directions because this is, yep.
How much, like, let's say we get to this point of the equation and then we mess up just to do the calculator. How much is it, if we get to here, it's pretty good, right?
Yeah, you're going to lose full marks just for calculator.
Okay.
No, I'm just kidding. I'm just kidding. You're not going to. The mark, if you set up the equation like this, which by the way, it really helps if you state the equation before you plug numbers into it so that we can see that you set it up right, and then make a calculator error in one of the 1, 2, 3, 4, 5, 6 terms in this that you have to plug into your calculator, there's not going to be a lot of marks deducted because I don't think it's reasonable. The solution I gave, I did this in a spreadsheet. You know, in real life, you probably wouldn't do this by hand. You do this in a spreadsheet so that you don't do calculator errors, and maybe you want to play around with the numbers, that sort of thing. So yeah, don't worry about, okay, well, worry about calculators. Don't make calculators because that's free marks basically that you should be able to get. But we'll be looking for an equation like this, very nicely stated with the signs outlined. That will be most of the marks for each of the directions. I think that's fair. So I'm not going to do the other directions. You have the solution to this problem. I think if you go through this problem and get all of the signs right in the setup, maybe if you're very worried about calculator, you can practice putting into your calculator. Remember, the angles should be in degrees. That will be another error that several of you will make. Then you'll be able to get this. So this is just practice. I would do this practice for the final. So I'm going to talk about the CV subtleties now. So in particular, so in this question I emphasized just now, our CV encompasses the pipe. So the pipe is within our CV. So any forces applied to the pipe are forces applied to our CV. There was an example I did in this lecture. This was for the non-uniform flows lecture. So you remember we did this example with the porous section of a pipe with a non-uniform mass flux. The CV for this question actually didn't encompass the pipe. It encompassed something like this. I'm going to do this in a bit bigger. So the green box was our CV. So the reason that we know that in the real world, there will be viscous forces. This is a porous wall at the top. So there'll be viscous forces applied to the fluid at the pipe wall there. But this question said neglect those viscous forces, neglect wall friction. So that CV then can be placed just inside the pipe wall. So the pipe applies no force to our CV, and our CV applies no force to our pipe. Does that make sense? The only forces that we did in the force balance for this question, if you look at the summation of forces here, we're just worrying about the fluid. So we only did pressure forces. And that's because our CV doesn't include our pipe. So if we were to include our pipe, we would have additional unknowns. Are there any questions about that? And again, the thing that allowed us to do this in this question is neglect wall friction.